Me all right? Perfect. Okay. So for our last speaker of the winter school, it's my pleasure to introduce Gabriele Matzeu. He's currently affiliated with ENAF in Bologna and also with ESA, and he's going to be telling us about some new stuff he's been doing with a program called XRADE. So please take it away.
Thank you very much. I have to say, first of all, that thank you, Peter, to invite me. This is a great, I mean, it was a great experience because mainly I can just see the application of BXA that I really would like to implement it in the work I'm going to present. Okay, so, well, this is XRADE stands for X-Ray Accretion Disk-wind Emulator. So in this project, essentially, all started when I was in Madrid doing like the first lockdown. So I had a lot of spare time. So I basically took over this project. And then I literally, by going to this project, I then realized I went into the machine learning world, which is completely something that I would never expect. So one great thing about this is like, you can never really tell what your future holds, because if you would ask me like 3 years ago, if you'll ever be into like machine learning, I would say, of course not, meaning that I'm usually do X-ray spectroscopy. So, but yes, so this is the world. These are my collaborators. There are many more. And this was started first of all with the implementation of basically theoretical model, but in Athena and Chrism. So how do I change that side? It doesn't work. To do that? No. Okay. Well, you got the magic hand. Well, bye. Thank you very much. And yeah. So on this side, yeah. Yeah. So okay. So what I'm basically doing. Well, I just want to give you a little introduction. Okay. So XRADE is essentially is basically a theoretical model that well accounts for what we call ultra-fast outflows. Okay, so I just want to give you a little bit of introduction for the non-experts. So around 10 years ago, or a little bit more now, there was this great discovery in science that every galaxy, or the vast majority of galaxy, if not all galaxy, holds a supermassive black hole in the center. Now, the other discovery, which is straight follow that, it was really puzzling, because what they found is that a tight correlation between the mass of the hosting, of the black hole hosted, and then the velocity dispersion of the stars in their galactic bulge. So in simpler terms, what they see was a correlation between, well, there was basically the larger galaxy also hosted the more massive black holes. And this was incredibly puzzling, okay, because, and somebody also can tell you still is, because basically the sphere of influence, okay, of the supermassive black hole is incredibly smaller than the rest of the galaxy. So we're talking about, the size, let's say we're talking about 1 million to 1 billion times smaller, but also the mass of the supermassive black hole is like, 100 or 1,000 times like smaller. So the big question was how these two vastly different quantities know about each other, because you see, as you can see there, well, the correlation, this is it's been observing so many things. I mean, the correlation is there. It's been a lot of authors. These were the first one, but then there are a lot of authors. They keep looking, and that correlation is always there. So, well, so how these two quantities knows about each other? How something like of the size of a coin knows about the rest of the world, let's say. So the plausible basically hypothesis, well, is that there are what we call ultra-fast outflows, and the ultra-fast outflow or X-ray winds, we can call in different ways, is exactly what I am doing. So this doesn't work again. I may do something wrong with this. The other. Well, he's so yeah. So shall I do it by hand? It's working. So it's me. I got. Maybe. Okay. I'm gonna go really fast. Okay. No. Okay. So we see here basically the scales. Yeah. Well, this is obviously artistic impression. This is the scale we are talking about. So this is where the winds are basically generated. Okay. So this could be it could be the most plausible like link that basically. So a lot of material gets pushed out, and then it basically it provides feedback to the rest of the host galaxy. Okay, so how do we see these ultra-fast outflow? What is their imprint? Is basically, well, we observe them in the X-ray spectra as basically really defined absorption features. Okay, and then obviously the absorption feature, it can tell you which element obviously we are looking at, and also they're very highly ionized. Okay, so but also the other thing that we can see from the absorption features is that there is like a Doppler shift. Okay, they are essentially blue shifted. So, and the degree of this blue shift gives us, well, an idea of the outflow velocity. Okay, so this is very important because then we can, in theory, we could measure the power of this wind. So the outflow velocity that we do observe, they go from 0.1 so to 10% to like 30–40% the speed of light. So they're really powerful things. So in this talk, I'm going to talk about ultra-fast outflow, which are wind outflows. They're all the same thing. Okay, so I was still a PhD student. So in 2015, so there was a great breakthrough, okay, in this science. Essentially, for the first time, we observed basically the prototypical ultra-fast outflow, which is PDS 456. PDS 456 is the most luminous quasar in the local universe. But what really makes it special is that because it's so luminous, obviously we get a good quality data, but also hosts the most powerful and persistent wind yet observed. So this was the first time we actually used XMM and NuSTAR together. Okay, so this really revealed some really important things. So for the first time, because of NuSTAR can give you obviously the data above 10 kV, so the real continuum, the level of the continuum was actually revealed. Like if you, I mean, let's say that before then, if you extrapolate, if you had only like XMM, he was like here. So the true level of the continuum was revealed, but also, really importantly, we have, we have the absorption, but also we have a very broad emission. So obviously people say, okay, if you got a material, if you got a wind, so you obviously observe an absorption feature, but the emission in this case is essentially the scattered photons of the wind. Okay, and because it's basically average from all angle, so a broad emission, it basically means that the covering factor of this wind is really high. Okay, so this is called the P-Cygni light profile. So, and it's been now observed in other AGN, but essentially that's what this comes from the same gas. Okay, so and because of this, for the first time, we could directly measure the mass outflow rate. Okay, and with that, and the solid angle and the velocity inferred from the degree of blue shift, we could calculate the kinetic power, which are extraordinary. Okay, so and is well beyond what is required for a wind to create like a feedback. So yeah, that was a great result. And so yeah, so okay, so my study now, because now we know that the signature of the wind is not just in absorption, but also in emission. So I took over this code that was, I call it the Disk-wind code, and it was developed initially by Stuart Sim in 2008, but then it was almost forgotten. So because I had this idea that the wind is basically ubiquitous, the reason why we don't sometimes see it is because it's out of the line of sight. So the fact that now we can observe the scattered emission as well. So this code was the perfect thing for us. So yes, so the geometry here on the Disk-wind is essentially we see well, we assume a biconical wind with an opening angle of 45 degrees, and then we have we set up a launching radius, and also, you know, the thickness of the wind. So this is really important because essentially we try to assume a more realistic geometry of this wind instead of having like a spherical assumption. So here the empty spaces are as important as the material. Okay, so with this code we can actually calculate for example the velocity of the wind. We can have a direct measurement of the mass outflow rate, and then in each grid in each point, in each cell, it calculates also self-consistently basically the ionization state of the wind. So it really, as you say, it's probably wrong, but this is at least is a more realistic wind. Okay, but very importantly also, in every cell we calculate 20 different line of sight. So either if we observe the wind here or we observe inside, so we can measure something called the inclination angle, which now we will see that profoundly affect the actual spectra. Okay, so I always get the wrong one. Okay, so this is like a color map of the wind and of the Disk-wind. So as I said earlier, because it calculates in each cell the ionization state. So, and this is the ions. Okay, so we have at the base of the wind, it's pretty Compton thick, and then, you know, the ionization becomes higher and higher if you go further out. But let's say I took 3 cases, okay? If the line of sight, if we observe above the wind, so essentially we don't observe directly into the wind, what happened is we got 3 different components. So we got the total, obviously, we got the transmitted component and the scatter component in green. So here we see that the transmitted component is completely flat, but we see that what is dominating here is the scatter component, which makes sense because if you look above the wind, all you see is the scattered photons. So the presence of the wind can be actually seen just by the scattered photons. So, and I basically used this model to basically model a source which is considered a bare AGN, TON S180. And I can see that basically the wind is there, but is out of the line of sight. So then if we be going through the wind, you can see that the transmitter component is full of absorption feature. But then when you look at the base of the wind, you see that the transmitter component is basically surplus, but you have a very strong scatter component because he's basically at the base of the wind is Compton thick. So here to really give you, so if you put like the NH of the material and to the inclination angle, we can see that obviously as soon as you start, and because we got the opening angle of 45, as soon as you start reaching 45, 46, 47, we can see that is increasingly really drastically. Okay, so it's very much angle dependent in terms of the viewing angle. So yeah, okay, so what I did for the CCD, so for XMM, I generated 2 different grades with 2 different launching radius, but essentially I simulated something like 17,000, anyway, that number. But essentially, this is been, I want to publish these 2 as soon as these 2 tables, as soon as my paper comes out, and yes, so I enlarge, I mean, there is a great parameter space, and so far so good. So that was in itself a result, okay? But things start changing when I started working with the Athena people, and it was required, okay, so it was asked, okay, but if we're gonna have Athena, if we're gonna work with Athena, what can you do? What kind of spectra you could do, or the disk-wind, what the wind spectra would look like? So because I think that the disk-wind is a great is a great thing. So what I did, I basically simulated, I basically made some high resolution, basically disk-wind spectra, 2 electron volt. And basically you can see the incredible details, the Athena resolution, but the very important thing is also that the shape of the absorption feature is actually asymmetric. Okay, so this, I'll tell you straight away, is because it's a simulation. Obviously, the real spectra of you know, the real thing is not going to be so sharp, but is kind of helping, and also because I'm heavily involved with the magnetohydrodynamically driven wind, which is a little bit different. We can see that with Athena, actually, if you look at the MHD wind instead of the radiatively driven, you can see that the shapes are actually reversed. Okay, I don't want to go into much details because we're still in work in progress of why, but so for the first time now with Athena, we will be able to basically disentangle if you know the driving mechanism and the launching mechanism. I still believe that they both radiatively and MHD, I mean, they're all together. I think they're both combined, but so great, Athena, oh my God, it's just the best. But the thing though that really caught my attention is that there you have the CCD like a resolution, and there you got the micro-calorimeter. So look, to create a grid point with like 40 cores, it takes around 2 hours. But here, when I did the high resolution, and it wasn't even, it was just like a very, very easy, it was just with all predefined like parameters. It was, it took 16 hours, 14, 16 hours. So I thought, here we are in trouble, because if essentially we want to match our model to the Athena resolution, well, to basically run, I mean, the one that I already did for the CCD, it took me like 7 months, okay, to run like with the same details as this one for a high resolution. It would take years, literally years. Okay, so this was a bit of a worry, but and this is the point where I basically I knew about emulation, and I had to approach my colleague at the time, like Magilu, which Isa, and she obviously does all she does. So essentially I said, okay, you need to help me here because I really don't know how we're going to do it. So yes, so we got into the machine learning. So we essentially, I'm sure that a lot of you knows even more about me than this, but I just really quickly. So basically machine learning, you want to map. It's useful that if you have an input, you want to map that to an output that basically resemble or is basically similar. So basically the machine learning, that's what you do. You train some data, and then you map this input into an output. So the simplest form obviously is this connector here. So here you have the weights, you have a bias, and basically this is like a straight line. Okay, so this is the most simple connector, but obviously because we're not interested in straight line, we want to have we want the training of a much more complex, obviously much more complex feature. So we have what is called an activation function, which ensure a non-linearity. So as I said earlier, I have all the spectra available. So 80% we train. Then we had the 10% for the validation to see how good the fits are. But then we got that 10%, which is just for testing. So the network did not see this. So did not see these 10%. So in the future plots, I'm gonna show you, basically that come from the true spectrum, come from this 10%. Okay, so we build a network. And this network is comprised of three hidden layers. So we got the 6 input, and then we have these 1,000 output, which is in energy beam. So for the high resolution, we would have something like 10,000. But what I try to say that essentially how we constructed this was purely trial and error. Okay, I am learning as I go along. So it's never been done before, I think, but this is what we found that was basically, it was okay for this kind of reason. So we then had different activation function to ensure a non-linearity. And the one that we chose was the ReLU. Okay, so ensure that all the outputs are positive. So anyway, we basically chose this. Again, we can choose a different one, but this is what, for this work, that's what we chose. So this is the result. Essentially, we have, well, the orange spectra is essentially the truth value. So from the 10% testing, and the blue spectrum, which sometimes you cannot see, is actually the emulated spectra. So it comes from the network. So these are, so you can see the gray result here. I mean, there is doing pretty good job from 0.1 to 511 kV, because we want to include all the physics. But these are 48 out of, so they're basically randomly picked. I could pick other ones. So these are completely random, the way I picked them. So actually the accuracy is, we found that is within 10%. So the other thing that we noticed that was really useful, and it's going to probably be a game changer, is that, as you know, sometimes XSpec, what he does has what we call the interpolation problem. So what is an interpolation problem? So you have a model. So if you got like a grid, right? You got 2 grids. So you got 2 essentially values. And then you get another measurement which comes in between. So the interpolation, what it does the mean essentially. But in practical term, what happens is that essentially you get an hybrid spectrum. So you get something that is in between, especially if the model is actually is really sensitive to these kind of things. So in this case, so we did like, so in the first row and bottom row essentially are absorption feature in the ion K that are very, well, one is a very broad feature and the other one a very narrow feature. I wanted to show the kind of two extremes, but we see that if there is only one, the interpolation in one parameter, then the interpolation can do okay. So it's just between a parameter, two values of the same parameter. So it takes the mean, but we see that the emulation does a little bit of a better job. And so, yeah, so far and so good. But really, when you fit in X-ray spectra, you always have more than one parameter a free. So when we start increasing the number of parameters that interpolates, you see here that in the ion K, the interpolated is basically, it doesn't really match very well. And also, if you go to 3D or 4D, it gets worse and worse. But you see that the emulation actually does a good job, and it's not perfect. But the reason why it's not perfect is because I'm gonna tell you a little bit later, because you got some errors, some fractional errors, which is nothing to do with this. But you see, he does a better job. So what this is telling us is it's telling us that in the future, instead of creating some really fine grids that takes a long time, we can have essentially, well, we can model in a framework that we don't have interpolation problems. So even though the model is a bit coarse, we can be sure that we have an accurate measurement. Okay, so this is the problem we actually had. That when we look at the fractional error across the 0.1 to 511 kV, so we notice a spike here. We notice a spike here, and then a spike, some of the spikes there. And guess where these are from? Are from the energy band where the wind is more, well, you see the action of the wind. So there is a lot of variability. It's where basically the action happens. So so obviously we can see that what we did needs more work. I mean, is doing an okay job. So if you look for example, this is like the outflow rate. We see that, you know, it's not quite perfect. Like, so here as well, we see that it struggles a little bit. So the improvement we thought to do was to essentially, well, one of the improvement, and then I'm gonna put it out there. If you got some other improvements I can do, I welcome them greatly. So we go like a random sampling. So instead of creating a grid, we actually create, we have a range of parameter space, and then the sampling is completely random. So maybe that helps. And also, well, that is really importantly, we're gonna do more, well, higher resolution sampling. So between the energy band where the wind has more variability or where the action happens, we do a finer sampling, a finer training. So this is one of the two. It's gonna be in the next paper, but what you can see here in all of this, you can see that at least the normalization is actually, I mean, he's well estimated. So he's just about to tweak in a couple of things. So I'm just gonna show, really, that was the figure, the P-Signy-like profile earlier on. So to do that basically that feat of the absorption and the emission, essentially we needed two separate models. two extra models, which is a photon ionization code and assuming a spherical geometry. So with this, we can do it with just one XRADE, with just one model. We can do both the emission and the absorption. And the value that we get out, they are really, really good. I mean, we can say that they are completely consistent with what we found before. So yeah, so the great thing about this work is that essentially well, I didn't plan this, but what it looks like here, that we have a tool, right? We have a tool that is gonna be able to transpose or to bring all the current models that we use with CCDs to basically bring them or match the high resolution that we're gonna have with like XRISM and Athena. Because believe it or not, when we have such advance in technology, everything has to match that. So the great thing about this is like you can do a very large table within minutes. So for example, to basically simulate, well, to emulate one spectrum, it takes a fraction of a second instead of like 10 minutes or 50 minutes for high resolution. So I think this could be a great tool and to basically implement. So I will implement it with MHD wind. I'm gonna implement it with another wind, but also, you know, I would like to obviously implement this to other non-wind model. So it would be, I mean, it would be just incredible to be able to basically match the Athena resolution. And also I want to use BXA. I want to see how I can implement BXA when I compare different models. So yes, thank you very much.
Thank you, Gabby, for a very nice talk. So I would like to first open up questions to anyone in the room. Yes, we have. Maybe if you come here, I think the further the microphone gets away, the worse the connection gets, unfortunately.
So really nice work. I mean, it's impressive. It's just if I understand this correctly. So essentially, what you are doing is, I mean, you have a model of ultra-fast outflows with the resolution of XMM or whatever. So you have like 150,000 models that you can, and with that you train 80% of that you can train a neural network to the rest. Yeah. So the idea is to use that idea in Athena, right? So since you cannot simulate, you cannot calculate the vast number of due to the resolution. So my question is, okay, this works very well because you have a very large training sample. Essentially, you can calculate a lot of models for that. In the case of Athena, I mean, the idea is to reduce the computation time. So you have an estimation of what would be the percentage of your parameter space or number of spectra that you need to calculate to reach a similar thing?
Well, that's the thing. Because we won't have interpolation issues, what we hope is that when you're doing the first simulations, like I call it the original simulation, what we hope is that we can afford to have a bit of a more space, so we don't have to go really thin. So that means that, you know, we don't have to spend a lot of time. But even if we do spend a lot of time, first of all, we can do any section. But even if we spend a lot of time, it will be just once, because then after this trend, you can produce any wind in Matzeu. So it's still in work in progress, but I think we are on the right direction. Yeah. I can say we're on the right direction. Thank you.
there any other questions in the room? Yeah, Jakob, maybe if you come to us. Yeah, sorry, just for the microphone.
Yeah, so I understood that you're obviously pioneering this kind of method in our field, but I can imagine that this kind of approach is already like also applicable somewhere else outside of X-ray astronomy, or maybe even outside of physics. So if you can comment a little bit on how safe it is to use this, or how much like pioneering work is it? Is there any dangers, or is there anyone else who does it in some other field?
I can tell you that as far as I know, nobody else is doing it, and obviously that's why I'm really open for suggestions, because even the person that did machine learning, because she works on basically on galaxy cluster and identify, all the things that you do with machine learning. So this has never been applied before, but we can see that is working. So yes, the idea is to even apply outside the X-ray astronomy. Is something that can help us. Obviously, we need to be careful, because you can see that there are some errors, and we need to implement. We need to improve it. But yeah, I think the idea is to apply even outside, and to essentially reduce computation time, to do something that, but also, for instance, there is this great program called FreeML that essentially you can feed the data outside XSpec. And that also is going to be great, because we don't have the interpolation problem. So we can, but essentially, yes, I would like to be applied outside as well. And I think it's pretty safe, but, I still don't know 100%.
But like you are not even aware that someone else is doing it at the moment for some other problem.
Nobody else is doing it, and that I take the word from like Maggie, which is the machine learning. I mean, I'm take the word for it, but I'm pretty sure that nobody did that. Okay.
Are there? Yes, Johannes. Maybe.
So from people who've done these kind of emulators on supernovas and particle physics, I know that there are sort of two approaches to setting up these emulators. One is, so at each energy you have an output. The other approach is you have an additional input, which is the energy, and only one output, so that you tell, oh, where do you want the output to come out? I was just wondering which of those two methods you chose. So the many output one.
I've got the 6 inputs.
Okay.
Essentially the parameter from, and then the output, is the energy. So in this case, only 1,000. Okay. We know that, but yes, we would like to increase that with Athena, so to 10,000, but it's going to take longer. Okay. But if you think there's other ways to improve, I'm absolutely open. I'm open.
No, actually, I think the other approach is much more difficult to train, and this one seems to behave better.
If I may just quickly ask a question. So you showed the plot with fractional error. And you showed some preliminary fits as well. I was just curious, do you know how this level of fractional error, or do you know some level of fractional error you'd like to get to reach the parameter uncertainties that you would want in the final spectra with XIFU, for instance, if you know what I mean?
Well, I think I would hope at least within the 10%. At least within the 10%, but I actually would like to go even lower. That's at least within 10%. Because here, look, it's just crazy. I mean, it goes to another level. So yeah, hopefully.
Okay. Do we have any questions on Slack, on Zoom? Does anyone have any comments or questions? If not, then let's